In our last class, we were looking into SJF policy. So, we start with an example of this SJF policy. Suppose we have got 4 processes in a system at some point of time when the scheduler is running. So, it has to take a decision like which process will be executed next, and their arrival times are like this 0, 2, 4 and 5, and their CPU burst times are 6, 8, 7 and 3. Now, SJF policy. So, how do we know this burst time value? So, that is an issue, but definitely we are not considering that. So, suppose we know these values, then as far as the SJF policy, the whichever job has got the shortest burst time, so that will be selected. So, the job, so this is the smallest value. So, P4 is scheduled. So, P4 runs from 0 to 3 time unit, and from 3rd time unit P1 is the next job that we have whose burst time is just larger than P4 and smaller than others. So, P1 executes for 6 time units, followed by P3 for 7 time units, and then P2 for 8 time units. So, overall completion time is 24 for the set of jobs. So, throughput if we compute, so we have completed 4 jobs in for 24 time units. So, throughput is equal to 4 by 24. So, that is 1 upon 6. So, 0.166. Okay. So, 0.166, that is the throughput. So, that is there. Now, this average waiting time. So, this is basically this is average waiting time is equal to this first job does not, the job P4 does not wait. So, the waiting time is 0. P1 is waiting for 3 time units. So, this is 3. P2 is waiting for 16 time units. So, that is 16, and P4 is waiting for P3 is waiting for 9 time units. So, that is 9. So, average waiting time is 3 plus 16 plus 9 plus 0 divided by 4. So, that is equal to 7. Now, if we try to see the effect of this set of job when they are scheduled on a FCFS, first come first serve basis, then P1 will be scheduled at the beginning. P1 came first. So, P1 gets scheduled from time 0 to time 6. So, here I have got P1, then from 6 then came P2, and that requires 8 time units. So, this is 8. So, this is our P2. So, 6 to 8, that is 14. Then comes P3 for 7. So, this is P3 for 7. So, this is 21, and then P4 for 3 time unit. So, P4 came after that, and P4 for 3 time unit. So, this is 24. So, that is P4. So, you see that the set of tasks. So, this is completed at time 24 only, but under this FCFS policy. So, if you compute this throughput, so throughput remains same. So, throughput is equal to 4 by 24, that is 0.166. However, if you try to see what is the average waiting time. So, for P1 the waiting time is 0, for P2 the waiting time is 6, for P3 waiting time is 14, and for P4 waiting time is 21. So, 6 for 20 plus 21. So, 41. So, this is the total waiting time. So, average waiting time is 41 by average waiting time is 41 divided by 4. So, that is 10.25. So, you see that the average waiting time for SJF policy was equal to 7, and for FCFS policy. So, this is going to 10.25. So, this way if we are going for SJF policy, we can see that this waiting time can reduce significantly, and as there is a theoretical proof that says that you cannot beat this time 7, that is you cannot come up with any other scheduling of this P1, P2, P3, P4 such that the average waiting time will become less than 7. Okay. So, that is the idea. So, we can but the difficulty with this SJF policy is that how do we know what is the next CPU burst time. Okay. So, the FCFS we did not have any problem because arrival time of the jobs are known, like when the job came to the system, or if it has gone for an IO burst. So, next when it joins the ready queue, so that time is that time can be found out from the system clock. So, we can find out which job joined the queue at what time. But this how much time the job will execute in the next CPU burst before going to an IO operation. So, this is not possible to tell accurately, and it also depends on the execution trace that we have in the program. So, for the programmer also it is not possible to tell the size of the CPU burst, because that will depend on the actual execution sequence. Maybe for some data values it will be doing a lot of computations, and some other data values maybe it will be just bypass many of those computations. Okay. So, as a result this is it will depend on the value. Like say a typical example is the loop statements. Like if I have got a loop like for I equal to 1 to n do. So, this so how many times this loop will execute. So, that depends on the value of n. So, if in one CPU burst maybe the n value was equal to 10. So, it executed for some time without doing IO operation. In the another CPU burst maybe n value is equal to 1000. So, naturally the CPU burst sizes are not comparable that way. So, for the user also it is not possible to tell. So, we have to so we cannot implement this SJF directly, but SJF being a very good policy, we can try to do some approximation of that. So, next we will see an approximate technique that will try to be close to SJF, and that will try to predict the behavior of the process. Okay. So, that it is known as the shortest remains it will try to predict the next CPU burst size. So, what is done here is that we try to estimate or predict the length. Okay. Now, it can be observed that if I have got a program which is doing some computation, some scientific computation, then it is very much likely that if in one time, if one CPU burst, so it has used say 20 time units, then in the next CPU burst, after that it has done a small amount of IO, and after that it is going to another CPU burst. So, this CPU burst time cannot be largely different from 20. So, it cannot be that the next CPU burst is very small, or the next CPU burst is much larger than the original than the previous CPU burst. This happens because this whole the CPU bursts that we are considering. So, they are part of the same process and they are doing similar computations. For example, maybe it is getting some data, and based on that it is doing a set of computations. So, it is very much unlikely that this the computation duration will vary significantly. Of course, there may be some data values for which it will change, but in general it will not happen. So, this how to predict. So, we try to do a prediction. Okay. So, based on this 20 value, we try to predict what is the next value, or to be on a safer side, what we do is that we consider last few CPU bursts. Okay. So, you take so this is from the beginning of the program, maybe this is the size of the CPU burst 1, after that we had some IO burst, then we have got another CPU burst C2 of some duration, then we have got some IO burst. So, this way it goes on. So, previously, so in this way if you have got up to the CPU burst size Cn, then the IO burst, and then if you are trying to predict like what is going to be the size of this CPU burst. So, we take the history into consideration, that in recent time, so it has generated the CPU bursts of size C1, C2 and up to Cn. So, based on those values we try to predict the CPU burst size for the Cn plus 1. So, that is the prediction. So, what we do is, suppose Tn is the actual length of the nth CPU burst. So, this nth CPU burst, if this duration was equal to Tn, the size of this burst was equal to Tn, then tau n plus 1 is the predicted value of the next CPU burst. So, this is our prediction. So, this is not the actual one. So, until and unless this CPU is given to the process for execution, so we cannot know what is the value of T n plus 1. So, this is not known, this is not known, but the previous value T n is known, because when the CPU was given to the process last time, how long did it use it. So, that value is the T n value. So, that value is known, but T n plus 1 is not known. So, we what we try to do is that we try to predict the value of tau n plus 1. So, we try to predict the size of the next CPU burst. So, we say that tau n plus 1 is basically alpha time T n plus 1 minus alpha time tau n, where tau n is basically the prediction that we had at this point. So, for this burst, so what was, so suppose this burst was predicted like this, so that was the value of tau n, and it actually executed for this T n. So, for this nth CPU burst, the prediction was tau n and its actual execution was T n. So, we try to take an average of these two. So, basically, so this is alpha times T n plus 1 minus alpha time tau n. So, if you expand this expression, then you can see, so this is alpha times T n plus 1 minus alpha into alpha time T n minus 1 plus 1 minus alpha times tau n minus 1. So, this is alpha times T n plus alpha into 1 minus alpha times T n minus 1 plus 1 minus alpha square into tau n minus 1. So, again this tau n minus 1 can be expanded. So, essentially what I am getting is an expression like this, alpha times T n plus alpha into 1 minus alpha times T n minus 1 plus alpha into 1 minus alpha square into T n minus 2 plus alpha into 1 minus alpha cube into T n minus 3. So, that way it goes on going up to T 1. So, you see in this expression of tau n plus 1, so we are considering the actual CPU bursts over last n cases, okay, and based on that we are trying to see like what is going to be the next CPU burst. So, but their weights are decreasing. So, the recent burst, so it has got the maximum effect. So, this alpha is a value between 0 and 1. So, this 1 minus alpha is also a value between 0 and 1. So, as you are going away from the current CPU burst, so the weightage of this weightage of that CPU burst is decreasing. But so whenever you are trying to predict the size of this n plus 1th CPU burst, then you are we are giving this T n the maximum weightage, that is alpha time T n, but the previous to that the T n minus 1. So, that is given less weightage than T n, because it is alpha into 1 minus alpha into T n minus 1. So, this weightage is less. So, as you are going back and back, so this weightage is reducing, the weightage on that burst size is reducing. So, this way we try to make a prediction, and this whole part, so this whole part is captured by this term 1 minus alpha into tau n. So, what was the prediction at the nth burst. So, this way we can have some prediction for the n plus 1th burst of the CPU, and then n plus 1th CPU burst for the process, and accordingly we can take a decision. So, if we have got say processes say P 1, P 2 and P 3 in the ready queue. So, for each of them we know their tau value. So, tau 1 n plus 1. So, this is we have got the prediction for this one also, tau 2 n plus 1, and this one also tau 3 n plus 1, and we use these tau values to take a decision like which process should be scheduled next. Now, this value alpha that we have is between 0 and 1, and you can understand that this alpha value. So, if alpha is set to be equal to 0, if alpha is set equal to 0, then tau n plus 1 is equal to tau n. Okay. So, whatever you have as the initial prediction, so that continues. So, this the history does not have any effect on the CPU on the prediction of the next CPU burst. Whereas, if you take alpha to be equal to 1, then this part does not have any effect, and we have got this tau n plus 1 is equal to T n. So, the next prediction is made to be equal to the actual CPU burst time that we had in the previous burst. So, that is T n. So, it is just considering history of one previous burst. So, it is not considering all of them, it is just taking one burst and taking it as the prediction. So, tau n plus 1 equal to T n. So, we have got so these are the two extremes. So, ideally we should be somewhere in between. So, alpha is normally set to half or 0.5, and that puts equal weightage on the previous frames, previous CPU burst size and the previous CPU burst prediction. And that previous CPU burst prediction, in its expansion we have seen that it has got effect of all the previous CPU burst times in actual. So, this way this shortest job first algorithm, so it can be approximated, and this is very common. So, whenever a job is executing, so we note down how much was the CPU burst, how much time it executed in the CPU. So, as we have seen that with the CPU maybe after executing for 2 seconds it goes into an IO operation. So, in that case T n becomes equal to 2, or in some other case maybe after executing for 5 seconds the job goes into IO burst. So, T n value becomes equal to 5. So, this way based on those T n values, this tau n plus 1 can be predicted, and based on that prediction the scheduler can take a decision like which job to be scheduled next. So, that is the approximation to the shortest job first. So, this is alpha equal to 0. So, tau n plus 1 equal to tau n. So, recent history does not count. On the other hand, we have got alpha equal to 1. So, tau n plus 1 equal to alpha times T n. So, only the actual CPU burst counts, and as we expand it. So, this is this expansion we have already seen, and successive terms they will have less weight than its predecessor. So, this slide actually summarizes to what we have discussed previously in terms of this weight of this individual CPU bursts. So, suppose this is the actual CPU burst sizes. So, this blue line is the actual CPU burst sizes, and this these are the predictions. So, this is at time. So, the first CPU burst guess is so this is sorry, this the blue line is the tau values, the predicted values, and T value is the actual CPU burst. So, this is the sizes. So, initial prediction, so that is arbitrarily set to be equal to 10, and you see the actual time it took is 6. So, so actual time it took is 6. So, this as a result the next prediction comes down to 8. Okay. So, it is predicted to be 8, and so it comes here, but at that time the CPU burst was actually equal to 4. So, next time the prediction comes down to 6, okay, and this actual execution is also 6. So, it was fine. So, prediction remains at 6 only, but then the execution is 4. So, again the prediction comes down to 5. Now, the actual execution has jumped. So, the prediction was 5, that is here, but it has used 13 time units, and the CPU burst was of 13 time unit. Then a prediction will go up, and the next the prediction comes to be 9. Okay. So, it increases to this value. So, this becomes equal to 9. Now, for the next part also the CPU burst is high is 13 only. So, this it continues to be 13, and the prediction again goes up using that formula. So, this is equal to 11, it is equal to 11. Then it goes to a prediction of 12, and if it goes like this, then you can see that slowly it will catch up this value 13. Okay. So, this prediction that we are doing, so prediction is trying to follow the trend of the process. So, if the trend, so here it performed miserably because there was a sudden change in the behavior of the process. So, previously the CPU burst values were equal to 6, 4, 6 and 4, and all on a sudden it has become 13. So, this is the change in the behavior of the process. So, our prediction could not follow it, but after that the process has continued to behaving like this, the CPU burst size to be equal to 13, and this prediction value is slowly catching up that value. So, again so now the next prediction happens to be equal to 12. Now, if all on a sudden the process drops its CPU burst size, so process starts becoming more of IO bound job, then again the prediction has to come down, and it will take quite a few time steps to again catch up with the actual time. So, that is there. So, but it is a good prediction. So, we can see that is a good approach for doing the approximation via the prediction. So, another algorithm which is known as shortest remaining time first, or SRTN, or SRT. So, sometimes it is called SRTN. So, instead of first we call it shortest remaining time next also. So, then the algorithm will be called SRTN algorithm or SRTF algorithm. So, this is a preemptive version of the SJF algorithm. So, shortest job first, it tells that whichever job is has got shortest CPU burst, so that will be getting first. But so, if now a job comes and whose burst time is less than whichever job is currently running, then naturally suppose some job PI was running, and PI's CPU burst predicted CPU burst was say 15 units. So, this tau value was equal to 15. So, it has been selected and it is running in the CPU. Now, a new job PJ comes whose CPU burst, whose predicted CPU burst is less, suppose this is equal to 5. Then if this PI is executing and PI might have, out of this 15, maybe it has run for say 5 time units. So, it needs to run for another time unit to finish this 15, but this job PJ has come, so which is definitely shorter than this value 10. So, it is advisable that we take out PI and give PJ the CPU. So, that is exactly the concept that we have. So, we have got if we vary the arrival times then and apply this preemption policy, then we can have these things. Suppose we have got 4 processes P1, P2, P3, P4, their arrival times are 0, 1, 2, 3 and the burst times are 8, 4, 9 and 5. Now, at times so at initially this P1 came. So, when this scheduler was there, so at that time we had only P1. So, P1 came, so P1 got scheduled. So, P1 executed, so after that P2 came at time 1. So, when so at time 0 only P1 was there in the system. So, scheduler could not have any choice. So, it scheduled P1. Then after some time, after one time unit P2 has come. Now, when P2 has come, so the system sees that okay, the job that is running now is going to take another 7 time units and P2 is of burst time 4. So, P1 is preempted and P2 gets the chance for execution. So, P1 has executed for 1 time unit. So, it has got 7 units left. Now, P2 comes. So, P2 needs time for 4 time unit, but at time 2 P3 comes. So, P3 when it comes, so P3 its burst time is 9, but this has already executed for 1 time unit. So, the remaining time is 3, but it cannot. So, this P2 continues to be the shortest job. So, this P2 continues. Then after some time, after 1 time unit P4 comes, but here also the P2, so this P3 is waiting and P2 has executed for 1 more time unit. So, remaining time is 2, but P4 is of requiring 5 time units. So, they are not scheduled. So, P2 continues for 4 time units and it completes at time 5. So, this is time 0, this is time 1. So, this is up to time 5 it executes. Now, we have got 2 processes, 3 processes in the system P1, P3 and P4, and out of that P4 has the smallest remaining time. So, P4 gets scheduled. So, P4 executes and no further job comes. So, from this point onwards it is behavior is similar to SJF. So, P4 executes for 5 time units. So, it completes at time 10. Then between P1 and P3. So, P1 had 7 time units left and P3 had 9 time units left. So, P1 got scheduled. So, it executed till time 17 and then P3 got scheduled. So, P3 got executed till time 26. Now, the point is that this is a preemptive version. So, this whenever a new job comes, the scheduler will be invoked to check whether it needs to preempt the job from the CPU, the currently running job from the CPU and schedule the new one. Now, this is good, but at the same time you see that it is a bit the overhead is slightly more, because every time a new job comes to the ready queue, the scheduler has to be invoked, and though we tell that at this time, so P1 executes from time 0 to 1 and then P2 executes from 1 to 5, but what will happen is that in between the scheduler will be invoked. So, there some time will be spent in invoking the schedulers. Then again at time 2, P3 has arrived. So, at time 2 again the scheduler will be invoked to see whether it needs to do some switch over. Similarly, at time 3 the scheduler will be invoked to see if it needs to do any switch over. So, those overheads are there. So, though it is not shown in this diagram, so those overheads are there. So, as a result, so this is the theoretical behavior, but in the actual behavior, so those timing of the execution time for the schedulers are to be taken into consideration, and as a result the duration will be more. So, the shortest remaining time first. So, this is a good algorithm, because it is also taking care of the job which is running in the system, but of course, with the catch that it is quite complex strategy as far as execution implementation is concerned. So, this out of the algorithms that we have seen so far, FCFS implementation is very easy, because I can have a FIFO data structure, like queue type of data structure, and then in that queue whenever a new job comes, it joins at the end, that tail end, and whenever a job has to be taken for execution, so it is taken from the front end. So, we do not really need to remember the arrival times also with the job. So, if we follow that policy, it is very simple, but the remaining policies, so it is slightly difficult, because we have to take care of this other information like their burst time, their priorities and all. So, that makes it difficult. So, even for this SRTN algorithm, so we have to take care of these policies. So, in this way, so we can have different scheduling policies. Now, we can have some other policies, which is one of them is the round robin policy. So, this round robin policy, we have got some small time quantum, and the job is executed for some time quantum q, and when the time quantum expires, then the job is taken back from the CPU and the next job gets the time for execution. So, we will see that this type of policy, so this is good if you have got an interactive system or a multi user system, where each job should get attention for execution for some time. So, this is good for an interactive system, but at the same time we will see that the amount of time wasted is the maximum here, and the wait time and everything will go up for the processes. So, we will see that in the next class.